Welcome to this series of lectures on time series analysis. In these we will discuss different aspects of how one can model data that one has observed. For example, this data shows the number of people traveling by plane over time. If I recall correctly, the x-axis is months here, which also seems to make sense. We can see that there is an annual cycle in the travel. Typically, it seems people are traveling more in the summer, or perhaps it's the winter. We don't actually know without knowing more information about the labeling here. We can also see that there is an increasing trend in the data. More and more people are traveling every year. If you were asked to predict the number of people that will fly the next month, say that you were working on scheduling air traffic, how would you go about it? Clearly you should expect that there is a growing trend, so our prediction ought to make use of that. And we should also have some way to include the annual cycle in the data. Note also that the variability of the cycle seems to grow every year. We want to include this too. So how do we do this? Essentially, this is what we will learn in this course. The first step will be to divide the data into a modeling data from which we construct our model, say up to here. Then we want a set of data where we can test the model that we are building. We call this the validation. Let's say that this is the data up to here. We need this validation data to see if our model can be useful on data we have not observed before. Note that it's easy to make a perfect model on the modeling data. We can just have the model being one parameter per sample, making each sample describing that data point. That would make that model describe the data perfectly. But this would be a bad model, as it would not work on new data. This is why the validation data is so important. It allows us to test how small a model we can get away with and still have a good prediction on the validation data. The last part of the data is our test data. This is saved for the final evaluation of the model. Typically, when building a model, one goes back and forth comparing the validation data over and over again, and then modifying the model accordingly to improve it. This test data is used as a clean data set that you have not seen or used at all before in your modeling, and then it's used for the final evaluation of your model. For this reason, you should never touch the test data until you're done. If you change the model after examining the performance of the test data, you have no way of evaluating that change, and you fool yourself to believe that you have improved the model without actually being able to test if you have done so. When your employer then wants a prediction, you use the model that you have developed, but of course you use the most recent data to form your prediction. But you do not change the model from the one you built using the model and the validation data. Here's another example. This figure shows the date of the break of the ice of the Tanara River. Looking at the data, it seems like we can be able to see that the ice breaks earlier and earlier every year. But is this really so? And is this a statistically significant change or just a minor variation? It's easy to draw a line through the observation and then draw strong conclusions from that. The line we see here must surely show that there is the global warming effect. Or does it? To determine this, we can estimate the line using the observation. That is, we form y is equal to kx plus m, estimating the k and the m from the data we have observed. But whenever we estimate something, there will always be a variability in our estimate. It is theoretically impossible to estimate things with zero error. So our estimate will always be like this. So our estimate of k will be the true value of k, but within some confidence interval, and the same thing for the m. Say that these confidence intervals are wide. This means that the line could be within a very large range, and then could see something like this. That means that any line within that region would be statistically significantly the same as any other line, meaning that this line would be the statistically equivalent of the line we have drawn. That would yield a very different conclusion if that was the case. In this particular case, the confidence intervals are quite narrow, so the conclusions we drew were indeed correct. We are seeing the effects of the global warming in this data. But it is important to be aware how easy it is to give an erroneous impression if the confidence intervals are not given. It's not enough to provide an estimate or a prediction. You also have to give the quality of the estimate. Otherwise, it's not much value to it. Let's say that you ask me to predict the share price of Ericsson 1 hour from now so that you can know if you can trade in the share or not. This is really easy. I can, for instance, say that it will be, say, 100 kroners. But if I don't add that this is plus minus 50 kroners, you might well trust the prediction and make a trade. But if you know that how uncertain my prediction is, you likely will not. The difficulty of making a prediction or estimate is not to make it. The hard part is to make it accurate. Here's a further example. This is a snapshot of the wave heights during the Hurricane Bonnie, with quite some significant waves showing up. If you are to build a harbor, or say an oil platform, or you just want to go sailing, it would be quite important for you to be able to predict the possibility of extreme waves. How likely it is that you get a 10-meter wave that would break that new bridge that you're building? This is a problem of predicting extreme, which is outside of the scope of this course, but that is highly related to our studies. Note that the data here is two-dimensional, but this is basically just means that we have another index to keep track of, and that we have matrices instead of vectors and so on. We will discuss how to deal with this kind of data later on in the course. Here's another example. This is a synthetic aperture radar of an oil spill in the Yellow Sea. From aerial pictures it's difficult to see oil on water, but if you use radar this is not a problem. A synthetic aperture radar works like this. You fly your airplane along a given trajectory, but aim the radar at the same point of the ground with each transmission. Then you rearrange the data to form a so-called synthetic aperture. This means that you arrange the data so that it appears that you only send a single pulse, but measure the reflection along the entire flight path at once. As the width of the array determines the resolution in the image, you can get a high resolution image of the ground even if you are very far from the observed area. For instance, if you sit outside reading, we could with the current technology tell if you are reading the textbook with blue or green cover from space. Obviously you can look at other things than oil. If you change the frequency of your radar transmission, you can for instance set it to reflect on leaf canopy. In this way determine how much of the rainforests that are cut down. You could not do so using an aerial picture as the rainforests are always covered by clouds. But this is not a problem for radar. As an alternative you could set it to reflect larger objects below the canopy, for instance to look for vehicles hiding in the forest. As you can guess, there are quite a few people interested in such applications out there.